So how exactly do you stop a 50-mile wall of fire that is consuming everything in its path, and how do you do it when the nearest road is completely cut off? First, let's talk about the scale. We are looking at a mega fire raging through the rugged terrain of the Sierra Nevada or the Australian bush. This is a critical situation because once a blaze reaches this magnitude in this kind of geography, traditional firefighting methods become instantly obsolete. You see the fire trucks parked helplessly at the base of the cliffs. The crews are standing by, but they simply can't push up these vertical inclines. The fire is moving faster than they can drive, feeding on dry timber that hasn't burned in decades and confronting them with flames towering 30 meters into the sky. At this point, humans are just too small. But the real surprise is the weapon of choice deployed to fight this beast. Unlike the urban fires we often see controlled by hydrants and hoses, this operation relies on heavy amphibious aerial firepower. Suddenly, a silhouette drops from the smoke, skimming just feet above a nearby lake. This isn't just a plane, it's the Super Scooper, a machine that turns the very geography of the battlefield into its ammunition depot. But to understand why this specific aircraft is the only hope, we have to look at why these wildfires have become nearly impossible to defeat with boots on the ground. To understand why this specific aircraft is the only hope, we have to look at how the environment itself is conspiring against the firefighters. The geography here is divided into safe zones and death zones, and unfortunately, the fire loves the death zones. We are talking about rugged, inaccessible wilderness, places like the steep canyons of the Sierra Nevada or the dense, roadless expanses of the Yukon. This terrain is a nightmare for logistics. Just as military operations struggle in swamps or dense jungles, firefighting operations crumble when the topography turns vertical. Ground vehicles, no matter how powerful, face a simple physics problem. Heavy bulldozers and Type 3 fire engines cannot navigate slopes steeper than 40%. In these deep ravines, the gradients often exceed 60%. If a truck tries to push up there, it risks rolling over or getting trapped in a box canyon with no escape route. But why is the fire so much more dangerous in these canyons? To understand this, we have to look at the fire triangle: heat, fuel, and oxygen. In a flat field, a fire radiates heat in all directions. But in a V-shaped canyon, the heat from one side radiates across to the other side, preheating the vegetation before the flames even touch it. This preheating effect causes the brush to ignite explosively, almost instantly. Worse, the wind acts differently here. It doesn't just blow over the fire, it gets funneled. This is known as the chimney effect. Just like a fireplace drafts smoke up a chimney, these narrow valleys channel superheated air and embers rapidly uphill. Security analysts and meteorologists have observed fires in these conditions moving faster than a human can run, sometimes climbing thousands of feet in minutes. This creates a tactical deadlock. You can't send crews in because you can't get them out fast enough if the wind shifts. So, the strategy shifts to air support. But why are the traditional aircraft unsuccessful in stopping these mega fires? They face various problems from payload limitations to cycle times. Let's look at the standard helicopter. You often see them carrying those orange Bambi buckets slung underneath. While they are agile, they are limited by physics. A standard helicopter can only carry a few hundred gallons of water. Against a fire releasing the energy equivalent of a small nuclear weapon every hour, that is like trying to put out a bonfire with a squirt gun. They have to fly to a water source, hover, fill up, fly back, and drop. It is a slow, methodical process that loses momentum against a fast-moving blaze. Then you have the heavy hitters, the large air tankers, or LAATs. These are converted passenger jets like DC-10s or 737s filled with fire retardant. They carry a massive payload, painting red lines across the ridges to create chemical barriers. But they have a fatal flaw: logistics. These massive jets cannot land on a lake. They are tethered to major airfields with long runways and specialized reloading equipment. When they drop their load, they have to turn around and fly all the way back to base. In remote fires, that round trip can take 45 minutes to an hour. During that hour, the fire is left unchecked. It burns through the retardant line, jumps the gap, and keeps growing. The fire doesn't take a break while the tanker is refueling. Furthermore, intelligence gathering is difficult because the fire creates its own smokescreen. The visibility in these canyons can drop to zero, creating a blinding fog of ash and carbon. High-flying jets can't see the targets clearly, and flying low in a jet aircraft through a twisting canyon is a suicide mission due to their high stall speeds and lack of maneuverability. Additionally, the sheer heat output creates extreme turbulence. We are talking about updrafts strong enough to snap the wings off a smaller plane or flip a helicopter upside down. This effectively creates a no-fly zone directly above the heart of the fire for most conventional aircraft. So, the incident commanders are left with a broken equation. The ground is inaccessible. The helicopters are too light. The heavy jets are too slow to return. The fire operates in remote, difficult terrains that act as natural fortresses, shielded by wind and smoke. To break this siege, we need a machine that contradicts traditional aviation design. We need something that doesn't need a runway. We need something that can fly low and slow like a bush plane, carry the payload of a heavy truck, and maneuver like a fighter jet. We need a vehicle that can stay in the fight, hammering the enemy without retreating to base. We need a hybrid that bridges the gap between sea and sky. Let's take a closer look at how these aerial firefighters go about targeting a wildfire that ground crews can't reach. First, they establish command and control over the airspace. Just like a naval task force in the Gulf of Guinea, an aerial firefighting operation relies on a hierarchy of machines working in perfect unison. It starts with the Air Tactical Group Supervisor, often circling high above in a nimble, twin-engine aircraft like a King Air or an OV-10 Bronco. This is the quarterback of the operation. From high altitude, they provide the in the sky, managing the complex traffic of helicopters, tankers, and spotter planes, ensuring that everyone attacks the fire without colliding in the thick smoke. Next comes the target acquisition. Before the heavy bombers arrive, a lead plane dives into the canyon. This pilot is the pathfinder. They fly the exact run the tanker will take, checking for updrafts, power lines, and escape routes. If the line is good, they trigger a smoke system, trailing a stream of white smoke directly over the target area. This visual cue is the green light. It tells the tanker pilot exactly where to release the payload to have maximum effect on the fire's flank. Then, the heavy weaponry arrives. While converted jetliners have their place, the undisputed king of this specific tactical environment is the Canadair CL-415, widely known as the Super Scooper. Unlike the F-35s or MQ-9 Reapers that rely on distant bases, this aircraft is designed for sustained, close-quarters combat. The strategy here is not about a single, massive strike. It is about suppression through relentless frequency. This is where the Super Scooper fundamentally changes the logistics of the battle. In a traditional operation using land-based air tankers, the cycle is slow. A jet takes off, flies 20 minutes to the fire, drops its retardant, and then has to fly 20 minutes back to the airbase. Then, it spends another 20 minutes on the tarmac refilling its tanks and pressurizing the system. That is a 1-hour turnaround time. In that hour, the fire has time to recover, reheat, and push forward again. The Super Scooper eliminates this downtime. It turns the geography of the battlefield into a logistical asset. Instead of returning to a distant runway, the pilot simply looks for the nearest body of water. A lake, a wide river, or a sheltered bay in the ocean becomes an instant forward operating base. This capability allows for a tactic known as circuiting. The aircraft drops its load on the fire, banks hard, descends to a nearby lake, scoops up a fresh payload, and returns to the fire line in a matter of minutes. In a scenario where a lake is just 5 miles from the fire, a single Super Scooper can drop over 100,000 liters of water in an hour. That is roughly 10 to 12 drops compared to the single drop a land-based jet could achieve in the same time frame. When you have a flight of 3 or 4 of these machines working in rotation, they create a continuous, wet barrier that the fire simply cannot cross. They deliver a hammer and anvil effect. They cool the edge of the fire continuously, knocking the heat out of the fuel and raising the humidity in the canyon. This allows the ground troops, the Marines of this operation, to finally move in and cut the containment lines that will kill the fire for good. But the sheer efficiency of this cycle hides the extreme violence of the maneuver itself. To turn a flying machine into a high-speed water pump requires engineering that pushes the laws of physics to the absolute limit. But the brute force multiplier of this scooping mechanism is where the real magic happens. Let's take a look at how they change the tide of the battlefield from the inside out. The Super Scooper isn't just a plane that floats, it's a hydrodynamic anomaly. The most critical 12 seconds of the entire mission happen right on the water's surface. To refill, the pilot brings this 20-ton machine down onto the lake at speeds of 80 to 90 knots. That is roughly 100 miles per hour. At this speed, water feels as hard as concrete. The margin for error is razor thin. If the nose digs in too deep, the plane could cartwheel and disintegrate instantly. If they come in too shallow, the probes won't catch the water, and the mission fails. Underneath the fuselage, tucked away like the landing gear, are 2 small probes, each about the size of a human hand. These are the intakes. When the pilot engages the scoop lever, these probes extend into the rushing water. They don't use pumps or complex machinery. They rely on pure, brute force physics, specifically dynamic pressure. The forward momentum of the aircraft forces water into the tanks with incredible violence. We are talking about 6,000 liters, or over 1,600 gallons of water, rushing into the belly of the plane in just 12 seconds. To put that in perspective, that's enough water to fill a standard backyard swimming pool, but it's being loaded faster than you can blink. This violent intake creates a massive problem: hydrodynamic drag. Imagine driving a car at highway speeds and suddenly driving into a wall of molasses. That is what the pilot feels. It's like slamming on the brakes while simultaneously hitting the gas. The water grabs the plane, trying to slow it down and pull it under. The pilots have to physically fight the controls, using immense upper body strength to keep the wings level and the nose up. It is a wrestling match with physics, and if they lose, the plane flips. But the engineering marvel is that as the water rushes in, the aircraft gets significantly heavier. In those 12 seconds, the plane gains 6 tons of weight. That is a 30% increase in mass, happening almost instantaneously. For a normal aircraft, a sudden weight gain like that would destroy the lift-to-drag ratio and send it stalling into the water. To counter this, the CL-415 is equipped with massive Pratt & Whitney turboprop engines. These aren't just for speed, they are for torque. These engines provide the instant, raw power needed to drag that extra 6 tons out of the water and back into the air before they run out of lake. The wing design is equally specialized. It features high lift devices and a large surface area that gives it incredible lift at low speeds. This allows the Super Scooper to climb out of steep canyons fully loaded, clearing ridge lines by mere feet. It's a delicate balance of aerodynamics and hydrodynamics working in concert to defy gravity. Once airborne, the mission shifts from brute force to precision bombing. The drop system on the Super Scooper is not just a trapdoor that opens and hopes for the best. It is a computer-controlled release system that allows the pilot to shape the water. Depending on the fire behavior, the pilot can choose to dump the entire 6,000 liters in one massive salvo. This creates a water hammer, a concentrated column of water heavy enough to crush a high-intensity blaze and penetrate through the thick canopy to the forest floor. Or they can string it out. By partially opening the doors, they can paint a long, thin line of water, creating a wet barrier for ground troops to work behind. Furthermore, they have a secret weapon on board. They can inject a chemical foam concentrate into the water mid-flight. This turns the water into a sticky, soapy mixture. When it hits the trees, it doesn't just run off into the soil, it clings to the vegetation. This creates a smothering layer that cuts off the oxygen, preventing the fire from reigniting even after the water evaporates. And they do all of this while flying just 100 feet above the treetops. This is Nap of the Earth, flying at its most extreme. They are battling updrafts from the fire that can toss the plane around like a toy, smoke that reduces visibility to zero, and heat so intense it can warp the aluminum skin of the aircraft. The cockpit of a Super Scooper is a chaotic environment. Alarms are blaring, the airframe is vibrating from the turbulence, and the pilots are constantly communicating with the spotter plane and ground crews. It requires a level of situational awareness that rivals that of a fighter pilot in a dogfight. The defensive layers of this aircraft aren't missile jammers or armor plating, they are its rugged construction and redundant systems. Everything is built to survive in an environment that tries to tear aircraft apart. The engines have specialized filters to keep out ash and debris. The hull is reinforced to withstand the constant pounding of the waves. It is a machine built for a war of attrition against the elements. Finally, disrupting the fire's logistics involves cutting off its fuel source. By wetting down the forest ahead of the flames, the Super Scooper breaks the chain reaction. It turns the fuel, the dry wood, into a non-combustible barrier. It starves the beast. Together, this multi-layered approach combines advanced aerodynamics with raw pilot skill to systematically break down the fire's energy, reduce its intensity, and buy time for the ground crews to finish the job. But even with these mechanical marvels, the true victory relies on the men and women in the cockpit. They are dancing on the edge of stall speed, surrounded by fire, performing a delicate ballet with a 20-ton machine. These missions are impossible without that human element. While satellites watch from space, these pilots bridge the gap between air and earth, turning water into a shield. But ultimately, even the most advanced hydrodynamics are useless without the courage of the pilot inside. These men and women fly into conditions that ground every other aircraft. They push these 20-ton machines to the absolute limit of their structural integrity, managing complex physics while looking down the throat of a firestorm. They do this to protect homes, history, and lives they will never know. They are the ones turning the cold science of fluid dynamics into the art of survival. They are the aerial dancers in a theater of fire. Only with this perfect union of man, machine, and bravery can the beast finally be tamed. We make original 2K 3D animations with a small team of creators, so please support us by subscribing and dropping in a comment for more exclusive engineering breakdowns made just for you.